Hey, sleepers! Tonight, we're going on a journey, a quiet and gentle journey, not across land or sea, but through the very fabric of the cosmos itself. We're chasing a ghost, a whisper, a particle so shy, so elusive, that billions upon billions of them are piercing through your body, through your bed, through the entire planet, every single second, without leaving a trace. We are going to explore the universe of the neutrino. Picture yourself now, just for a moment. You are floating in the silent, velvet blackness of space. Below you, the earth hangs like a beautiful blue and white marble, slowly, gracefully turning. You see the continents, the swirling clouds, the deep, dark oceans. But now, imagine you could see something more. Imagine you could see a constant shimmering rain, a river of invisible particles flowing from the sun, from distant stars, from the very beginning of time, washing over the earth and passing straight through it as if it weren't even there. That is the river we will be wading into tonight. So before you get comfortable, take a moment to like the video and subscribe. It helps this little corner of the universe continue to send out its signals. And while you're there, I'd love to know where you're listening from. Please share your location and your local time in the comments. It's always a wonder to see how far these stories travel, connecting us all in the quiet hours. So close your eyes, take a deep breath, and get ready to drift off as we explore the ghost particle that pierces the earth. Let's begin with the particle itself. What is this little ghost we are talking about? In the grand cosmic zoo of particles, the neutrino is one of the most peculiar. It is an elementary particle. That just means it's one of the fundamental building blocks of the universe. You can't break it down into anything smaller. It's like a single perfect grain of sand on an infinite beach. But this grain of sand is special. It has almost no mass. Imagine an electron, already one of the lightest things we know. A neutrino is millions of times lighter than that. It is so light that for a very long time, scientists thought it had no mass at all. It was a pure speck of energy, a fleeting thought in the mind of the cosmos. We now know it has a tiny bit of mass, a discovery that sent ripples through the world of physics. But we'll get to that part of our story later. For now, just picture something so light it's practically weightless, a dandelion seed on the cosmic wind. This particle also has no electric charge. This is incredibly important. Most of the particles you know, like protons and electrons, have a charge. Protons are positive. Electrons are negative. This charge is how they talk to each other. It's how they feel the electromagnetic force. It's why magnets stick to your fridge, why light bulbs glow, and why you don't fall through your chair. The atoms in your body and the atoms in the chair are repelling each other with this force. But the neutrino? It doesn't have this charge. It's neutral. So it completely ignores the electromagnetic force. It's like being at a very loud party where everyone is shouting, but you have perfect noise-canceling headphones on. The neutrino drifts through all the electromagnetic shouting and chaos without ever noticing it. It passes through walls, through mountains, through you, because the atoms that make up those things are mostly empty space held together by a force the neutrino simply doesn't feel. So if it doesn't feel electromagnetism, how does it interact with the world at all? It feels two other forces. One is gravity. Because it has that tiny, tiny bit of mass, it is pulled by gravity. But because its mass is so small, the pull is incredibly weak. It's like a single feather trying to change the course of a battleship. The other force it feels is called the weak nuclear force. As its name suggests, this force is, well, weak. And it only works over incredibly short distances. Distances smaller than the nucleus of an atom. So for a neutrino to interact with another particle, it has to get unimaginably lucky. It has to score a direct, perfect bullseye on the tiny, tiny core of an atom. The chances of this happening are infinitesimally small. A neutrino could travel through a light year of solid lead, and there would still be a good chance it wouldn't hit anything. A light year, that's the distance light travels in an entire year. It's a staggering, mind-boggling distance. And yet, this little particle can sail through it all without a care. This is why we call it the ghost particle. It is here, all around us, and yet it is almost entirely separate from our world. Think of it. Right now, as you lie there, breathing gently, about 100 trillion neutrinos are passing through your body. Every single second. 100 trillion. They come from the sun, from the nuclear reactions that power its fiery heart. They pour out, flooding the solar system. And they pass through you as effortlessly as a dream. They don't harm you. They don't change you. They don't even notice you're there. It's a bit rude, really. All these uninvited guests just passing through without so much as a hello. But they are a constant, silent reminder that there is a universe of activity happening on a level we can never perceive directly. Now, these shy little particles come in 3 different types, or as physicists like to call them, flavors. It's a fun name. It doesn't mean they taste like anything, of course. It's just a way to categorize them. The 3 flavors are the electron neutrino, the muon neutrino, and the tau neutrino. Each one is paired with a more familiar, heavier particle. The electron neutrino is paired with the electron. The muon neutrino is paired with the muon, which is like a heavier, unstable cousin of the electron. And the tau neutrino is paired with the tau particle, which is even heavier still. For most of our story, you don't need to worry too much about the differences. Just know that there are 3 kinds. And here's where it gets even stranger. A neutrino can change its flavor as it travels. An electron neutrino born in the heart of the sun can arrive at Earth as a muon neutrino. This is a phenomenon called neutrino oscillation. It's like a chameleon changing its colors as it walks along a branch. This ability to change, to oscillate, is the very thing that proved neutrinos must have mass. It's a subtle, beautiful dance that these particles perform as they fly across the cosmos at nearly the speed of light. It's a secret they kept for a very long time. So, to recap what we've learned so far, just before we drift into the history of their discovery. A neutrino is a tiny elementary particle. It has almost no mass. It has no electric charge. It comes in 3 flavors, and it can change between them. It interacts only through the weak force and gravity, which means it almost never interacts at all. It is a cosmic ghost, a silent messenger, a particle that connects us to the most violent and energetic events in the universe, precisely because it is so aloof and standoffish. It is a paradox. A particle defined almost by what it doesn't do. And yet, learning to see these ghosts has opened up a whole new window onto the universe. The story of how we came to know this ghost particle is a wonderful tale of scientific intuition and persistence. It begins not with a discovery, but with a puzzle, a deep, frustrating puzzle that was threatening the very foundations of physics in the early 20th century. In the 1920s, physicists were studying a type of radioactivity called beta decay. This is when the nucleus of an atom spontaneously changes. In the process, A neutron in the nucleus turns into a proton, and an electron is ejected. Physicists are, by nature, meticulous bookkeepers. They like it when the numbers add up. One of the most fundamental laws they hold dear is the conservation of energy. Energy cannot be created or destroyed. It can only change form. So, when they measured the energy of the atom before the decay, and the energy of the new atom and the ejected electron after the decay, they expected the numbers to match. But they didn't. Some energy was always missing. It was as if a thief was sneaking in during the reaction and stealing a little bit of energy, then vanishing without a trace. This was a crisis. Some great physicists, including the legendary Niels Bohr, were willing to consider that maybe, just maybe, the law of conservation of energy wasn't absolute. Maybe in the strange, tiny world of the atom, energy could just disappear. But one man, an Austrian theoretical physicist named Wolfgang Pauli, found this idea intolerable. Pauli was a brilliant, sharp-toned, and deeply insightful scientist. He believed that the laws of physics should be elegant and consistent. The idea of energy just vanishing felt messy and wrong. In 1930, he took a bold step. He wrote a letter to a group of his physicist colleagues who were meeting at a conference in Tübingen, Germany. He himself was not going. He famously wrote that he couldn't attend because he wanted to go to a ball in Zurich. In this now famous letter, Pauli proposed what he called a desperate remedy. He suggested that there was another particle being created in beta decay, a particle that was carrying away the missing energy. But to fit the observations, this particle had to have very specific properties. It had to have no electric charge, otherwise it would have been detected, and it had to have very little or no mass. It was, in his words, a ghost particle. He wasn't entirely confident. He ended his letter by saying he understood his idea was a bit wild, but that one must risk something. He even worried that he had proposed something that could never be detected. He called his hypothetical particle the neutron, but another particle was discovered and given that name soon after. It was the Italian physicist Enrico Fermi who later championed Pauli's idea and gave the particle its final name, the neutrino, which in Italian means little neutral one. For over 2 decades, the neutrino remained a ghost. A beautiful theory, a desperate remedy, but completely hypothetical. It was a particle that existed on paper in the equations of physicists, but not in the real world of experiments. Many thought it would never be found. How do you catch a particle that can pass through a light year of lead? It seemed an impossible task. But 2 American physicists, Clyde Cowan and Frederick Rains, were determined to try. They were masters of a new kind of big science that emerged after World War II. They realized that to have any chance of catching a neutrino, you need 2 things: an incredibly intense source of neutrinos and a very, very large detector. For the source, they turned to the most powerful neutrino factories on Earth, nuclear reactors. A nuclear reactor, through fission, produces a staggering number of neutrinos, trillions upon trillions every second, pouring out in all directions. For the detector, they designed a clever experiment. They built large tanks filled with water, with a chemical called cadmium chloride dissolved in it. The idea was that, very rarely, one of the neutrinos from the reactor would strike a proton in one of the water molecules. This interaction would create 2 other particles, a neutron and a positron. The positron would quickly find an electron and annihilate, producing a flash of gamma rays. The neutron would bounce around for a few microseconds before being absorbed by a cadmium nucleus, which would then also release a flash of gamma rays. So the signature they were looking for was two distinct flashes of light, separated by a few millionths of a second. It was a faint and specific signal, like looking for a single firefly that winks twice in a field full of other fireflies. In 1956, at the Savannah River plant in South Carolina, they set up their experiment. After months of painstaking work, filtering out all other possible sources of signals, they found it. They were detecting about 3 of these double flash events per hour. It wasn't much, but it was undeniable. It was the signal of the neutrino. They had caught the ghost. They sent a telegram to Wolfgang Pauli to tell him the news. He was overjoyed. His desperate remedy, his ghost particle, was real. It was a monumental achievement. For their discovery, Raines would receive the Nobel Prize in Physics nearly 40 years later in 1995. Cowan, sadly, had passed away by then. Their experiment was a triumph of ingenuity and perseverance. It proved that even the most elusive particles in the universe could be detected if you were clever enough and patient enough. But the story of the neutrino was far from over. In fact, a new mystery was brewing. This one came from the sun. The same nuclear reactions that power the sun, that give us light and warmth, also produce a huge number of electron neutrinos. Physicists had very good models of the sun. They could calculate with great precision how many neutrinos the sun should be producing. And so, they set out to detect them. An American chemist and physicist named Raymond Davis, Jr. built an experiment deep underground in the Homestake Gold Mine in South Dakota. He used a huge tank filled with over 600 tons of perchloroethylene, a common dry cleaning fluid. The reason for going deep underground was to shield the experiment from other cosmic particles that could create false signals. Only neutrinos could pierce the mile of rock above. Davis's experiment was designed to catch electron neutrinos. Very rarely, an electron neutrino would interact with the chlorine atom in the fluid, turning it into a radioactive atom of argon. Every few weeks, Davis would flush the tank and count the tiny number of argon atoms that had been created. His experiment ran for decades, and it consistently found something strange. It only detected about 1/3 of the neutrinos that the solar models predicted. This was the solar neutrino problem. Where were the missing neutrinos? Was our understanding of the sun wrong? Or was there something strange happening to the neutrinos on their long journey from the sun to the earth? This puzzle led to the creation of even bigger and more sensitive detectors. One of the most famous is the Super Kamiokande detector in Japan. It's a breathtaking sight. Imagine a gigantic cylindrical stainless steel tank, 40 meters tall and 40 meters wide, buried a kilometer underground. It's filled with 50,000 tons of ultra-pure water. And lining the walls, ceiling, and floor are over 11,000 golden, globe-like photodetectors, like the eyes of a giant insect, all staring inward. When a neutrino finally interacts with a water molecule in the tank, it can create a charged particle that travels faster than the speed of light in water. Nothing can travel faster than the speed of light in a vacuum, but light slows down when it passes through a medium like water. So it's possible for a particle to outpace it. When this happens, the particle creates a shock wave of light, a cone of pale blue glow called Cherenkov radiation. It's the optical equivalent of a sonic boom. The thousands of detectors in Super Kamiokande are there to catch this faint blue light. By analyzing the pattern and timing of the light, scientists can figure out the direction the neutrino came from, and crucially, what flavor it was. In 1998, the team at Super Kamiokande, led by Takaaki Kajita, announced a groundbreaking discovery. They were studying neutrinos created in the Earth's atmosphere when cosmic rays from space slam into air molecules. These interactions create both electron neutrinos and muon neutrinos. Because they are created in the atmosphere, they should be coming at the detector from all directions equally. But the Super K team found a deficit of muon neutrinos coming from below, the ones that had to travel all the way through the Earth to reach the detector. The electron neutrinos, however, were fine. This was the smoking gun. It suggested that the muon neutrinos were changing into another flavor, probably tau neutrinos, which the detector couldn't see as easily during their long journey through the planet. This was the first strong evidence for neutrino oscillation. A few years later, an experiment in Canada called the Sudbury Neutrino Observatory, or SNO, led by Arthur MacDonald, solved the solar neutrino problem once and for all. The SNO detector was unique because it used heavy water, which allowed it to detect all three flavors of neutrinos. And when they added them all up, they found that the total number of neutrinos coming from the Sun perfectly matched the predictions. The electron neutrinos that Davis was missing weren't gone. They had simply changed their flavor on the way to Earth. This discovery was revolutionary. It proved that neutrinos oscillate, and because of the rules of quantum mechanics, for a particle to be able to oscillate, it must have mass. The ghost particle was not weightless after all. It was a tiny but crucial detail that forced physicists to rewrite their standard model of particle physics, which had long assumed neutrinos were massless. For their incredible work, Takaaki Kajita and Arthur MacDonald shared the 2015 Nobel Prize in Physics. The ghost had been unmasked a little more, revealing a nature far more complex and surprising than anyone had imagined. And the tool they used, the idea of using a huge, natural, transparent medium to catch the faint flash of a neutrino interaction, would be taken to its most extreme and magnificent conclusion at the bottom of the world. Let's travel now, in our minds, to the most remote, most inhospitable, and most strangely beautiful place on Earth, the South Pole. Here, at the Amundsen-Scott South Pole Station, the world is a symphony of white and blue. A vast, flat, endless sheet of ice stretches to the horizon in every direction. The air is thin and so cold it can freeze your breath in an instant. The sun circles the sky for 6 months and then vanishes for 6 months of unending night. It is a place of profound silence and isolation. And yet, buried deep beneath the surface of this ice sheet is one of the most extraordinary telescopes ever built. It is not a telescope of mirrors and lenses. It doesn't look up at the sky. In a way, it looks down through the entire Earth to the cosmos on the other side. This is the IceCube Neutrino Observatory. IceCube is a monument to human ambition and ingenuity. It is a detector on a scale that is almost difficult to comprehend. Imagine a cube of ice, 1 kilometer on each side. A cubic kilometer. That's 1 billion tons of ice. This is the heart of the detector. But how do you build a detector inside a solid block of ancient ice? You do it with a giant hot water drill. From 2005 to 2010, a team of engineers, technicians, and scientists worked through the brutal Antarctic summers. They would drill a hole 60 centimeters in diameter straight down into the ice, 2.5 kilometers deep. That's deeper than the Grand Canyon. The drilling process for a single hole took about 2 days. and once the hole was filled with liquid water, they had a race against time before it froze over again. In that window, they would lower a long cable, a string, with 60 basketball-sized glass spheres attached to it. These spheres are the eyes of Ice Cube. They are called digital optical modules, or DOMs. Each DOM contains a highly sensitive light detector called a photomultiplier tube, along with all the electronics needed to digitize the signal and send it up to the surface. They lowered 86 of these strings into the ice, creating a three-dimensional grid of 5,160 electronic eyes, all waiting patiently in the dark, frozen silence. Why go to all this trouble? Why build a telescope at the South Pole? The Antarctic ice sheet is the perfect medium for a neutrino detector. First, it is incredibly thick, over 2 kilometers of solid ice. This massive layer of ice acts as a shield. It blocks out almost all the other particles from space, the cosmic rays that are constantly bombarding the Earth. These particles would create a storm of background noise for the detectors. But neutrinos, our ghost particles, sail right through the ice shield without any problem. So the ice filters out the noise, leaving a clean slate for the neutrino signal. Second, the ice at that depth is fantastically clear. It is some of the most transparent solid material on the planet. The pressure from the kilometers of ice above has squeezed out all the air bubbles, making it optically perfect. This means that the faint blue Cherenkov light produced by a neutrino interaction can travel for hundreds of meters through the ice before it is detected by one of the DOMs. This allows scientists to reconstruct the path and energy of the neutrino with great precision. The entire cubic kilometer of ice becomes the detector. It is a beautiful, elegant use of the natural environment to achieve a scientific goal. So let's picture what happens. For years, the 5,160 eyes of Ice Cube wait in the cold and the dark. Trillions upon trillions of neutrinos are streaming through the detector every second. Most do nothing. They pass through the ice, through the DOMs, through the entire Earth, and continue on their journey across the cosmos. But every now and then, maybe a few times a day, one of them gets unlucky, or, from our perspective, very, very lucky. A high-energy neutrino, traveling at nearly the speed of light, will slam directly into the nucleus of a water molecule in the ice. This violent collision creates a shower of other secondary particles. If the neutrino was a muon neutrino, it will likely create a muon. This muon, still carrying a huge amount of energy, will continue traveling in the same direction as the neutrino for up to several kilometers through the ice. And because it is charged and moving faster than light in the ice, it leaves a long straight track of that faint blue Cherenkov light in its wake. This track of light will spread out and be picked up by several of the DOMs along its path. The computers on the surface, which are monitoring all 5,160 DOMs constantly, will see this pattern. They'll see a cascade of hits, one after another, in a straight line. By measuring which DOMs lit up, and crucially, the precise timing of when they lit up to the nanosecond, they can reconstruct the muon's path. And from that, they know the exact direction the original neutrino came from. They can point back through the Earth to a specific spot in the sky. If the neutrino was an electron or tau neutrino, the interaction creates a more compact, spherical burst of light, like a firework exploding in the ice. This tells them the energy of the neutrino, but gives a less precise direction. Ice Cube can see both types of events. It is a true all-sky observatory, listening for the whispers of the cosmos in all directions at all times. And so the stage was set. A revolutionary detector, buried deep in the Antarctic ice, was operational. It was listening to the universe in a way no one ever had before. It was searching for neutrinos, not from our sun or our atmosphere, but high-energy neutrinos from the most violent and extreme corners of the cosmos. It was waiting for a messenger from a distant galaxy, a ghost particle that had traveled for millions or even billions of years to tell its story. The scientists waited, and they watched the data. And on a very particular day in 2017, their patience was rewarded. A single particle from an impossibly distant place arrived to change everything. The day was September 22nd, 2017. Deep beneath the South Pole, in the frozen, silent cathedral of ice, something happened. One of the 5,160 electronic eyes of the Ice Cube Observatory blinked. And another, and another. A wave of faint blue light, the ghost of the particle's passage, swept through a section of the detector. On the surface, in the Ice Cube laboratory, computers sifted through the torrent of data in real time. An automated system, a sophisticated algorithm trained to spot the telltale signs of a cosmic event, flagged something extraordinary. This was not a low-energy neutrino from the atmosphere. This was a monster. The computers calculated its energy to be approximately 290 trillion electron volts. That is an immense amount of energy for a single, tiny particle. It was about 30 times more energetic than the particles produced at the Large Hadron Collider, the most powerful particle accelerator ever built by humans. This was a particle forged in a cosmic furnace far more powerful than anything on Earth. And its direction was just as exciting. The track of light it left in the ice was long and straight, indicating it was created by a muon. The reconstruction showed that the particle had come from below the detector. It hadn't come from the sky above Antarctica. It had come from the sky above the northern hemisphere. To reach Ice Cube, this neutrino had traveled through the entire diameter of the Earth. It had passed through the crust, the mantle, the liquid outer core, and the solid inner core of our planet, a journey of nearly 13,000 kilometers of dense rock and molten iron, and had emerged into the Antarctic ice without slowing down. It was the ultimate ghost particle, piercing the planet as if it were empty space. The event was logged and given a name, as clinical and precise as the data itself, Ice Cube on 70922A. The Ice Cube system knew this was special. Within just 43 seconds of the initial detection, an automatic alert was sent out to the world. An email and a digital notice were blasted across the internet to a network of astronomers and observatories around the globe. The message was simple but profound. It said, essentially, we just saw a very high-energy neutrino. It came from this specific patch of the sky. You should point your telescopes there, now. This was the dream of a new kind of astronomy, a dream that had been decades in the making. It's called multi-messenger astronomy. The idea is to study cosmic events not just with one type of signal, like light, but with multiple messengers at once. Light, in all its forms, from radio waves to gamma rays, is one messenger. Gravitational waves, the ripples in space-time first detected in 2015, are another. And neutrinos are the third. Each messenger tells a different part of the story, like different witnesses to the same event. Light can be blocked by dust and gas. Gravitational waves are only produced by the most cataclysmic events, like black holes merging. But neutrinos, being so non-interactive, can travel directly from the heart of the most violent, dense, and obscured cosmic engines, carrying information that no other messenger can. The alert from IceCube was the starting pistol for a cosmic race. All around the world, telescopes began to pivot and stare at the patch of sky indicated by the Neutrinos path. One of the first to respond was the Fermi Gamma-Ray Space Telescope, a satellite orbiting the Earth. Its job is to scan the sky for the most energetic form of light, gamma rays, and it saw something. In the same direction that the neutrino had come from, Fermi detected a source of gamma rays that was flaring up, becoming unusually bright. The source was a known object, a celestial body catalogued as TXS05-06+056. This was the first crucial piece of the puzzle. A neutrino and a gamma-ray flare coming from the same place at the same time. Was it a coincidence? The odds were low, but more proof was needed. Soon, other telescopes joined the hunt. The Magic Telescopes, a pair of large observatories on the Canary Islands, also detected very high-energy gamma rays from the same source. Then telescopes that look at other wavelengths of light chimed in. X-ray telescopes, optical telescopes, radio telescopes, all of them turned their gaze to TXS 05-06+056, and they all saw it was in an active, flaring state. The evidence was overwhelming. This was no coincidence. For the first time in history, scientists had caught a high-energy neutrino from space and had successfully traced it back to its specific birthplace. They had found the cosmic accelerator that had shot this particle across the universe. The results were announced to the world in a scientific paper published in the journal Science in July 2018. It was a landmark moment, the dawn of a new era in astronomy. All because of a single fleeting track of blue light in the Antarctic ice. So what was this source? What is TXS05-06-056? It lies in the direction of the constellation Orion, but it is much, much farther away. It is a special type of object known as a blazar, and it is located nearly 4 billion light-years from Earth. This means the neutrino, and the light that arrived with it, had been traveling through space for 4 billion years. They began their journey long before the Earth had even formed. When they started, our solar system was just a swirling cloud of gas and dust. The journey of this single particle was a journey through deep time. To understand a blazar, we first have to understand what an active galactic nucleus is. Most large galaxies, including our own Milky Way, have a supermassive black hole at their center. These are black holes that are millions or even billions of times more massive than our Sun. Most of the time, these black holes are quiet. But sometimes, if there is a lot of gas and dust and stars nearby, the black hole will start to feed. A huge disk of matter, called an accretion disk, will form around the black hole, swirling like water going down a drain. As this matter gets closer to the black hole, it gets incredibly hot and bright, glowing fiercely in all kinds of light. This is an active galactic nucleus. Now, in some of these active galaxies, something even more spectacular happens. The intense magnetic fields and energy around the spinning black hole can grab some of the infalling matter and shoot it back out into space in two powerful, narrow jets. These jets blast away from the black hole in opposite directions, at speeds approaching the speed of light. They are some of the largest and most energetic phenomena in the universe. A blazar is simply an active galaxy, or one of these powerful jets happens to be pointed almost directly at Earth. It's like looking straight down the barrel of a cosmic gun. Because the jet is moving towards us at such incredible speed, its light is beamed and boosted in energy, making it appear exceptionally bright and variable. The Blazer TXSO 506 plus 056, the source of our neutrino, is one of these cosmic lighthouses. It has a supermassive black hole at its heart that weighs about 300 million times as much as our sun, and its jet is a colossal particle accelerator. Inside this jet, a violent storm is raging. Protons and other atomic nuclei are caught up in the magnetic fields and accelerated to phenomenal energies, far beyond what we can achieve on Earth. These are the particles known as cosmic rays. And here, in the jet of this blazer, scientists believe they have found the factory that makes both the high-energy gamma rays and the high-energy neutrinos. The leading theory goes like this: a high-energy proton, accelerated by the blazar's jet, collides with a low-energy photon of light, perhaps from the accretion disk. This collision is so violent that it creates new particles. One of these is a particle called a pion. Pions are unstable and decay almost instantly. A charged pion decays into a muon, and a muon neutrino. Then the muon itself decays, creating an electron neutrino, and another muon neutrino. So from one initial proton-photon collision, you get a shower of particles, including neutrinos. At the same time, the collision can also produce neutral pions, which decay directly into high-energy gamma rays. So this single mechanism naturally produces both the high-energy neutrinos that IceCube saw and the high-energy gamma rays that Fermi and other telescopes saw. It all fits together beautifully. The neutrino and the gamma rays are siblings, born from the same violent event in the heart of a blazer 4 billion light-years away. The discovery of the single neutrino in 2017 was so compelling that scientists decided to dig back into the past. They went through all the archival data that IceCube had collected since it started operating. They asked the question, has this Blazer TX SO506 plus 056 ever sent us neutrinos before? And they found something astonishing. In the data from 2014 to 2015, there was a period where IceCube had detected a significant excess of neutrinos coming from that exact same spot in the sky. Not just one, but a flare of over a dozen neutrinos, all clustered in time and space. At the time, this flare wasn't significant enough to trigger an alert on its own. But in light of the 2017 detection, it was a confirmation. This blazer wasn't just a one-time source. It was a known producer of cosmic neutrinos. This archival discovery added immense weight to the conclusion that blazars are indeed one of the long-sought sources of the highest energy cosmic rays. The ghost particle, by leading us to its home, was helping to solve a century-old mystery in astrophysics. The way that Blazer created our neutrino is just one of several ways the universe cooks up these ghostly messengers. Nature has a whole recipe book for making neutrinos, and they are a key ingredient in many of the most traumatic cosmic events. We've talked about the Blazer mechanism, a proton hitting a photon. This is what we believe creates the highest energy neutrinos that IceCube is designed to see. It's a process that requires a powerful particle accelerator, like the jet of a blazer, or perhaps a gamma-ray burst, which is an even more violent, short-lived explosion thought to be caused by the collapse of a massive star or the merger of two neutron stars. Anywhere you have protons being accelerated to extreme speeds, and a lot of light or other matter for them to crash into, you have a potential neutrino factory. But there is another, much more common, source of neutrinos that plays a fundamental role in the life and death of stars, the supernova. A supernova is the spectacular explosion of a star. For massive stars, this happens when they run out of fuel to burn in their cores. The core, no longer supported by the outward pressure of nuclear fusion, collapses under its own immense gravity. It collapses in less than a second, crushing all the matter down into an incredibly dense ball of neutrons. This collapse releases a truly staggering amount of energy. And here's the amazing part. 99% of that colossal energy is carried away not by the blast of light and matter that we see, but by neutrinos. As the core collapses, the protons and electrons are squeezed together to form neutrons, and in that process, a vast number of electron neutrinos are created. These neutrinos are briefly trapped in the ultra-dense core, but they eventually escape, carrying away the bulk of the explosion's energy. A supernova is the most powerful neutrino burst you can get from a single event. In 1987, astronomers witnessed a supernova in a nearby galaxy called the Large Magellanic Cloud. It was the closest supernova seen in centuries. And for the first time, neutrino detectors on Earth, including the Kamiokande detector in Japan, the predecessor to Super-K, detected a burst of about 24 neutrinos, just a few hours before the light from the explosion arrived. This was a historic moment. It confirmed the core collapse theory of supernova in stunning detail. The neutrinos, because they interact so weakly, were able to escape the dying star's core almost immediately, while the light was trapped behind the shock wave of the explosion for a few hours. The neutrinos were the first messengers to arrive, the advance warning that a star had died. These supernova neutrinos are much lower in energy than the ones from blazars, but they come in a much greater flood. If a supernova were to happen in our own Milky Way galaxy, detectors like Super Kamiokande would be overwhelmed by thousands of neutrino hits, giving us an unprecedented look into the heart of a stellar explosion. And there is one more source of neutrinos, the oldest and most abundant of all. These are neutrinos left over from the very beginning of the universe. In the first second after the Big Bang, the universe was an incredibly hot, dense soup of particles. Neutrinos were constantly being created and destroyed in perfect equilibrium with everything else. But as the universe expanded and cooled, the interactions became less frequent. After about 1 second, the universe became transparent to neutrinos. They decoupled from the rest of the matter and were set free to travel through the cosmos forever. This sea of ancient neutrinos still fills the entire universe today. It is called the cosmic neutrino background, or CGB. It is similar to the more famous cosmic microwave background, which is the leftover light from about 380,000 years after the Big Bang. But the cosmic neutrino background is much, much older. It is a snapshot of the universe when it was just 1 second old. These neutrinos are everywhere. There are hundreds of them in every cubic centimeter of space, including the space you are in right now. However, because they have been traveling for over 13 billion years, their energy is now incredibly low, making them almost impossible to detect with our current technology. Detecting the cosmic neutrino background is one of the ultimate holy grails of cosmology. If we could see it, it would open a window onto the first second of creation, a time that we can never see with light. So, from the fiery core of our sun, to the explosive death of distant stars, to the relativistic jets of blazars, and to the echo of the Big Bang itself, the universe is constantly producing these ghost particles. They are the quiet, unassuming witnesses to every major cosmic event. Each one carries a story, a message from its source. And by learning to read these messages, we are learning to see the universe in a completely new light. So why does this all matter? Why go to the trouble of building a billion-dollar detector at the South Pole to catch a handful of these ghostly particles from across the universe? The discovery of the neutrino from Blazar TX SO506+056 was not just a curiosity. It has profound implications for our understanding of the cosmos and the fundamental laws of physics. First, it helps to solve a mystery that is over 100 years old, the origin of cosmic rays. Cosmic rays are high-energy particles, mostly protons, that rain down on Earth from space. They were discovered in the early 1900s, but their origin has remained elusive. We knew they had to be coming from powerful cosmic accelerators, but we didn't know which ones. The problem is that cosmic rays are charged particles. This means that as they travel through the magnetic fields that permeate our galaxy and the space between galaxies, their paths get bent and scrambled. By the time a cosmic ray reaches Earth, it's impossible to tell where it came from. It's like trying to find the source of a river by looking at a single drop of water in the ocean. But neutrinos are different. They are not charged, so they travel in perfectly straight lines from their source to us. They are the perfect pointers. By finding a blazar that produces both high-energy neutrinos and gamma rays, the ice cube discovery provides the first direct evidence that these objects are indeed cosmic ray accelerators. It doesn't mean they are the only source, but it confirms they are a major piece of the puzzle. We can now say with confidence that some of the highest energy particles in the universe are forged in the jets of supermassive black holes. Second, neutrino astronomy gives us a new way to study the universe's most extreme environments. There are many places in the cosmos that are opaque to light. The core of a supernova, the region right around a black hole, the heart of an active galactic nucleus, these are places so dense and chaotic that no photons can escape. We can't see into them with traditional telescopes. It's like trying to see what's inside a locked room by looking at the closed door. But neutrinos, with their ghostly ability to pass through anything, can fly right out of these cosmic engines. They are our spies, our messengers from behind enemy lines. They carry pristine information about the physics happening in these otherwise inaccessible regions. By studying the energy and flavor of these neutrinos, we can learn about the temperature, density, and magnetic fields at the very heart of the universe's greatest powerhouses. Third, these cosmic neutrinos allow us to test fundamental physics at energies that are completely out of reach for any experiment on Earth. The Large Hadron Collider, LHC, at CERN is the most powerful particle accelerator ever built. It can collide protons at energies of about 13 trillion electron volts. But the neutrino that IceCube detected from the blazar had an energy of nearly 300 trillion electron volts. Nature's accelerators are far more powerful than ours. These cosmic neutrinos are a natural beam of high-energy particles that we can use to probe the laws of physics. For example, by studying how neutrinos oscillate over vast cosmic distances, we can test for tiny deviations from our current theories, which might hint at new physics. We can even use them to test Einstein's theory of relativity by checking if neutrinos and light from the same event arrive at the same time after traveling for billions of years. And finally, this opens up exciting new possibilities for studying some of the biggest unsolved mysteries in all of science, like dark matter. We know that about 85% of the matter in the universe is some mysterious, invisible substance that we call dark matter. We don't know what it is, but we can see its gravitational effects on galaxies and galaxy clusters. One leading theory is that dark matter is made of a new type of particle that, like the neutrino, interacts very weakly with normal matter. If two dark matter particles were to collide and annihilate each other, they could produce a shower of other particles, including high-energy neutrinos. So, neutrino telescopes like IceCube are also searching for a telltale of neutrinos coming from places where dark matter is expected to be concentrated, like the center of our galaxy or the Sun. A detection of such a signal would be a revolutionary, Nobel Prize-winning discovery. Neutrinos could be the key that finally unlocks the secret of dark matter. The discovery of the blazar neutrino was more than just finding one particle. It was a proof of concept. It showed that multi-messenger astronomy is not just a dream, but a powerful reality. It marks the beginning of a new chapter in our exploration of the universe. One where we listen to the cosmic symphony, not just with our eyes, but with a whole new set of senses, each one telling us a different part of the grand story. Catching these neutrinos is, as you might imagine, an incredibly difficult task. The technical challenges are immense. It is the ultimate needle-in-a-haystack problem. For every 1 billion high-energy neutrinos that pass through the IceCube detector, only about one will actually interact with the ice and produce a detectable signal. The other 999,999,999 just sail on through. So the first challenge is simply one of scale. You have to build a detector that is big enough to give you a reasonable chance of seeing anything at all. That's why IceCube is a cubic kilometer in size. If it were any smaller, it would detect cosmic neutrinos so rarely that it wouldn't be very useful. But even with a giant detector, there's another huge problem: background noise. The universe is a noisy place. IceCube is constantly being hit by particles that are not the high-energy cosmic neutrinos it's looking for. The biggest source of this background noise comes from our own atmosphere. When cosmic rays, the protons and other particles from space, hit the upper atmosphere, they create a shower of secondary particles. This shower includes a huge number of neutrinos, called atmospheric neutrinos. These atmospheric neutrinos can also have very high energies, and they can create signals in IceCube that look very similar to the cosmic neutrinos. In fact, IceCube detects an atmospheric neutrino about once every 6 minutes. It detects a truly cosmic neutrino from a distant source only a few times per year. So the detector sees about 100,000 times more atmospheric neutrinos than cosmic ones. The challenge is to tell them apart. This is where the scientists who work on IceCube have to be very clever. They use two main methods to distinguish the signal from the noise. The first is energy. On average, the neutrinos produced in blazars and other cosmic accelerators are much more energetic than the ones produced in our atmosphere. So, one of the main strategies is to look for events that have an exceptionally high energy, far above what you would expect from an atmospheric neutrino. The 290 TeV neutrino from 2017 was a perfect example of this. It was so energetic that it was very unlikely to be from the atmosphere. The second method is direction. For the one-track events, IceCube can reconstruct the neutrino's direction with a precision of less than a degree. One of the cleanest ways to look for cosmic neutrinos is to look for neutrinos that are coming up through the Earth. The Earth itself acts as a giant filter. It blocks almost all the other background particles, like muons created in the atmosphere, but it lets the neutrinos pass through. So if IceCube sees a very high-energy particle coming from below, it's a very strong candidate for being a cosmic neutrino. Even with these methods, identifying the signal is a monumental task in data analysis. The 5,160 DOMs in IceCube are constantly sending data to the surface, creating about a terabyte of information every single day. Sifting through this data to find the few interesting events is impossible to do by hand. This is where modern computing and machine learning come in. The IceCube collaboration, which includes hundreds of scientists from all over the world, develops sophisticated computer algorithms to automatically scan the data. These algorithms are trained on simulated data. The scientists create computer models of what a cosmic neutrino signal should look like, and what all the different types of background noise should look like. Then they use machine learning to teach the computer to tell the difference. It's like teaching a computer to recognize a specific type of bird by showing it thousands of pictures of that bird and thousands of pictures of other birds. Over time, the computer learns to pick out the subtle patterns and features that define the signal it's looking for. It is only through this combination of a massive detector, clever analysis techniques, and powerful computing that the discovery of cosmic neutrinos is possible. Reconstructing the properties of the neutrino, like its energy, is another challenge. It relies on carefully counting the photons of Cherenkov light that are detected by the DOMs. The more energetic the neutrino, the more particles are created in the collision, and the brighter the flash of light in the ice. By measuring how many DOMs saw the light and how much light each one saw, scientists can work backward to estimate the energy of the initial neutrino. It's a complex process that requires a very detailed understanding of how light travels through the Antarctic ice. Scientists have even lowered special calibration devices into the ice to measure its optical properties with extreme precision. Every part of the process, from the initial detection to the final scientific result, is a testament to meticulous, patient, and collaborative scientific work. It's a global effort to listen to the faintest whispers of the universe. The detection of the neutrino from Blazar TXS0506 plus 056 was a beginning, not an end. It has thrown open the doors to a new field of astronomy, and the future is incredibly exciting. The success of IceCube has spurred on plans for an even bigger and more sensitive detector. The proposed expansion is called IceCube Gen 2. The plan is to add thousands more optical sensors, increasing the volume of the detector by a factor of 10. With a detector that large, scientists expect to see not just a handful of cosmic neutrinos per year, but hundreds or even thousands. This will allow them to create a detailed map of the neutrino sky. They will be able to pinpoint many more sources, like blazars and gamma-ray bursts, and study them in detail. It will turn neutrino astronomy from a field of exciting but rare discoveries into a true systematic observatory of the high-energy universe. And IceCube is not alone. There are other neutrino telescopes being built around the world, designed to complement its view of the sky. IceCube, being at the South Pole, has a perfect view of the northern sky by looking down through the Earth. To see the southern sky, you need a detector in the northern hemisphere. 2 major projects are underway to do just that. One is KM3NET, which is being built deep in the Mediterranean Sea, off the coasts of France and Italy. Instead of using ice, it will use seawater as its detection medium. The other is the Baikal GVD telescope, which is being built in the deep, clear waters of Lake Baikal in Siberia. Together, these 3 giant detectors, IceCube, KM3NET, and Baikal GVD will form a global network, providing 24/7 coverage of the entire sky, watching for neutrinos from every direction. It is a new age of exploration, not of new lands, but of a new cosmic frontier. What mysteries might this next generation of neutrino telescopes solve? We have already touched on some of them. They will help us create a complete catalog of the cosmic ray accelerators in the universe. They will give us unprecedented views into the hearts of supernovae and active galaxies. They could potentially detect the signal of dark matter annihilation, finally revealing the nature of this mysterious substance. But there may be even more exciting discoveries waiting for us. Because neutrinos can travel from places that are completely hidden from our view, they might reveal entirely new types of cosmic objects, things we haven't even imagined yet. Every time we have opened a new window on the universe, from the first optical telescopes to radio telescopes and X-ray telescopes, we have been surprised by what we found. Neutrino astronomy will be no different. There are surely surprises waiting for us, hidden in the faint signals carried by these ghost particles. As we bring our journey to a close tonight, let's return to that quiet, peaceful image we started with. Picture yourself again, floating in the velvet darkness of space, watching the Earth turn below, and see again that shimmering, invisible river of neutrinos, flowing constantly from the sun, from the stars, from the edge of the universe. They are passing through the planet, through you right now. They are a connection, a physical link between you and the most distant, most violent, most ancient events in cosmic history. A particle that started its journey in the heart of a blazer 4 billion years ago has ended it in a flash of blue light in the Antarctic ice, its message finally delivered. It is a reminder that even the quietest, most elusive things in the universe have a story to tell. We just have to be patient enough and clever enough to listen. The universe is whispering its secrets to us. And with these magnificent new eyes, buried deep in the ice and the sea, we are finally beginning to hear them. So as you drift off to sleep, let the gentle river of neutrinos flow through you, connecting you to the vast, beautiful, and mysterious cosmos. Good night.